Click on this one, problem.
Sure. Which one?
Minus the 2.
Okay, let me pull it out. The last question.
Yes, ma'am.
Stay. So it changes the payment plans. And that actually means before the change, you can think of this as pretty much annuities and to right after that is what after that it's big. All on January of the year is 2003. The first one coming on 2011. You're getting Spain Q. In this case, Q is equal to 6160. Annual payment. So you're getting one payment here. In 2012, the payment becomes Q times 1 plus G. It's geometric progression at first. The G is equal to, at least online, is the 0.042. G may have given G percent. So keep in that same format for 2013. It will become Q times 1 plus G squared. Up to including the one on January 2024. So the mass of such payment is at 2034. If we compare the differences, this is 12, and there's a 1, and then there's 13, there's 2, so it's 11. So the last one would be Q times 1 plus G. 34 minus 11 is 20 power, right? That's the last one. Right? Okay. And then the one after is going to be 2075. And after that, increase $25 annually. So we have this amount. So this amount will still be there. The Q times 1 plus G to the power of 23 plus call that P. P equal to increase by that much every year, and then it continuing. I think we got a formula for the value of the perpetuity over here. Think of this as a perpetuity in arithmetic progression. We got formula from, I think it was Q over D plus P over I. Was that the formula for perpetuity?
It's the A double.
Right, that's the A double dot infinity. But it's for the one with P and Q. I guess there are I, P, Q before. So I think we should try to confirm the formula so I don't mess up the P and the formula. It would be that formula. Make sure I switch the order. Please. Update that. I think we can find out all of the two separate value at two separate time point and then deduct it back to the time, the current time. It's the activity formula. It's this one, right? This one. P over D plus Q over ID, but I switched P and Q because we have to, because we are not labeling things the same way. P is the initial payment, Q is the increment, but in this example, I kind of switched. So this formula will allow you to, this is supposed to be the initial payment, so it's like Q times 1 plus G to the power of 23 on my version, because that was the initial payment. So this will be calculated value over here, and you have to discount it back to the value at 2003. From 2003 back to 2003, the time is 32 years, right? So the calculation will be Q times 1 plus G to the power of 23 over the D. D is actually I times 1 plus I. Okay, and then plus they just use the notation is 425, so it's 425 over ID. So that's going to be I squared and then 1 times I. Right, this has to be discounted to current time. So you multiply that by 1 plus I to the power negative 32. So that's that perpetuity done. And then the rest of them, you have to calculate the value. These, the total number of many payment is actually 24 payment. These 24 payment is a is not perpetuity as annuity in increment order. It's a geometric sequence. You have to set up a formula, I guess. So far, this is the first half of the calculation, and the second half we would do discount process. We can find its value at, let's see here. Find value at time 2011. It would be the value Q plus Q times 1 plus G times B, that discounting this value back to this time, and then Q times 1 plus G squared, and then times B squared. You have to do this into the last one, which is one in 2034. But because I'm counting the 2035 in the calculation already, so this one has been counted in this annuity. So I'm seeing the 1, 2, so 23 is 23, and then plus that one, 24 payment. And then this is gonna be, the last one is Q times 1 plus G to the power of 23, and then we're gonna have to be 23. So that looks like a geometric summation. You take the common factor Q out, then it's 1 plus 1 plus 3b plus 1 plus G squared b squared. So that geometric sum will have 1 minus 1 plus G to the power of, there's 24 terms to the power of 24. And then B24 divided by 1 minus the ratio, which is 1 plus G times B. And that's the value at 2011, because I did that like discounting, right? So this number you have to discount it from 2011 back to 2001. You're going to multiply by a B to the power. It's 11 minus 8 power. I think that should be the calculation. I don't know if it helps because I might have different number than yours. So that's the discounting from perpetuity, because we have a later time. This is discounting from this annuity geometric sequence back to time 2003. The two added together have the value.
You discounted it back.
Yeah.
8 years.
Well, if this value is for 2035, I take the 35 minus 2003, that gives me, that's 32. Now this one, I started counting the value here at this time. That's why the first Q is not discounted. So that's 2011 value, so I have to minus 2003 to get 11 minus 3 is 8. So that would be power 3.
Okay, I just thought I saw it. Use that, but discounted it back. It discounted back 1 year prior to first payment.
This question, it says today is January 11, 2003. So coming back to 2003. But I'm not using formula for the geometric theory, because I really are calculating at 2011. All these cash flow, what is our value at 2011? I did this calculation using the geometric summation formula. So we don't have to worry about what was the time point of the calculation, because we set up the equation that way. And this one, we do have to worry about which one are we counting for the perpetuities. So this is plus needed. First payment. You make a point, right? If we're calculating this time, this is the initial payment, so we have to have a plus in this one. We're starting from this one. Save the statement. After that, the payment increased by 45. So 2035 is a little bit more than 2000. Because it's supposed to be the initial payment. In that perpetuity, the initial payment has added the 425. Should be part of the formula. Hope that answered your question, but try it again. If it still doesn't work, we can always talk about it after class. Hi, well, do you have any question? We're looking at the last question on the homework for sessions 373 and 39, and I hope that helps a little, because I'm trying to derive a formula for the computation bit. There's a change of payment plan. That's why we have to this interview. Do you have any questions? I was gonna go over this one, but I feel like maybe it takes even more time. Or if we have enough time to finish. This is an amortized schedule payment, but it's not a level payment. The payment has a increment. It's 2% lower than the prior payment. So then we're paying less and less in this plan. Questions to calculate the outstanding loan balance immediately after the 40s payment is made. So that will be the time point we're calculating the value of the balance at time 40 after the 40s payment. This is a monthly payment for 5 years. The 5 times 12, we have a total of 60 payment. After the 40s payment, the outstanding balance can be calculated by 2 ways. You either calculate summation of all the future payments, calculate the present value, or you calculate, if you look at the look back, it should be the loan that we borrowed minus all the payment that's already made. That's the outstanding balance. Okay, so if we are doing this calculation, then we're not given the outstanding loan balance. So the method we choose will be finding out the present value of all the future payments. So it will be taking on a prospective method. Or are you still working on that one?
Yeah,
Okay. Okay, so let's see if we're able to, wonder how much time it takes to finish this question, but maybe I can see this one and confirm the method later with a better written one. This is the question 7. So the one on the paper is trying to calculate outstanding loan balance. Right, if you look at the timeline, the total number of payment is, it says 5-year loan, and it says we are making monthly payment, 5-year monthly payment, then 5 times 12. We were supposed to have 60 payment. So here we have 60. Now the question is, how much was the balance after the in 60s is at 5 years. 40s payments, how many years? We don't know how many years. Months, right? Every year there's 12 months. So it's a little bit more than 3 years. 3 years, 36 months. We're trying to find the outstanding balance, the outstanding loan balance at the time. So the method we'll be using is try to find out the present value of all the future. This is talking about immediately after the 40s payment. That means after the 40s payment, we still have 20 payment, right? So there are 20 payment, and we have to figure out what exactly each payment is. So start from 0. Making payment monthly. The first payment is Q, and I'm writing Q because it's short. We're paying 1,000. And the second payment is 2 months later. is gonna be Q times 1 minus G, because we have a reduced payment of 2%. 0.02. You can also do 1 plus G, which is G being negative. Obviously, we try to come up with the following. That's 1 month, 2 months, right? And then at 3 months, it will be a payment of Q times 1 minus G squared. So there is a difference between the power 2 and the time 3. So with that in mind, I'm trying to come up with the actual formula for the value. That's why I'm trying to find the relation. At time 40, right after the time 40, that payment is Q times 1 minus G to the power 39. Right, that payment, it says immediately after the 40th payment, that payment has been made. But we don't want to calculate all the past payments. If you want to calculate past payment, you have to discount those payments value from the loan balance. In this question, we do not know the actual loan balance unless we calculate all 60 payments present value. That will be the loan payment, right? That will be a little bit extra time. So instead, we take a perspective view of it. We try to calculate this value. This is our time. At time 40, what is the value of all the future payment? That's our balance. Balance is the payment you still have to make from now on. So from here, the next payment would be at time 41, the payment would be Q times 1 minus G. And let me use a different color. Those are the payments that should be made. Only possible I use brown because we are already being made. So it's Q times 1 minus G to the power 40. That's going to be your first payment. And you have to discount it back to time 40, right? We're finding time 40 value. So I don't have a formula for this, so which is why we're using geometric sequence. So we're gonna have the first cash flow is Q times 1 minus G to the power 40. And we're gonna multiply V because we're finding its value at time 40, right? Plus the payment after that is going to be Q times 1 minus G to the power of 41. And then V squared is everything is discounted back to time 40. And then you have to keep doing this until the last payment. The last payment it will be Q times 1 minus G to the power of 59. Because we see that pattern, right? 2 and then 3. 1 and then 2, right? So at time 60, the power will be 59. We have to discount it back to, you see the relation, this is power 1, that's 41 and 2, 40 and 1. So the difference is 39. So we're going to take this 59 minus by 39, you're going to get 20. We kind of try to make sure that order all match up. Are we okay? And then this is really the total calculation for the outstanding loan balance. The outstanding loan balance is, there are two methods, either the present value of all your future payment or the future value of all your past payments discounted out of the loan balance in this, the current value of your loan balance. Subtract your past payment. There are two different methods, and we're using the perspective method, just calculating currently time 40 value of future payment. And now that's the calculation, and then the Q, the G, or the V depend on the interest rate. The interest rate is 9%. So our V actually 1.09 to the power -1 V. So we're going to factor all the common factor. The common factor is Q times 1 minus G to the power of, they all have power 40. So power 40, and then there's a V. And after that is 1 plus Q is factor. Oh, we have 1 minus G to the power 1, and then V to the power 1, and so on. You have to keep going until the last one, take out the 40. We have 1 minus G to the power of 19, and then V to the power T. So after you move out the common factor, you kind of see that finite summation in the geometric sequence. And then follow our formula, we have Q times 1 minus G to the power of 40 times B. And then 1 minus G times B in term 20 terms, total number of terms 20, so 20, and then B 20 divided by 1 minus G times B. 1 minus G is, G is 0.02, so G is 0.98. Basically, it's 0.98 over 0.09. I hope that was okay. And then the rest of the calculation, we're going to put it into a calculator. So let's see here. Try to review about how do we calculate outstanding loan balance. Is something we've done before. So here we have the Q 1000. So let's make it larger. 1000 times 1 minus G is 0.98 because G is 0.2. This raised to the power of 4. And then multiplied by B. B is 1.09 to the power of -1. Right. Then we have division. The denominator is 1 minus 0.98 over 9. That's the B and G. Numerator is going to be 1 minus this number of fraction to the power of terms. All right, and this is going to be a fraction of 0.98 over 9. Make sure the interest rate is percent. Oh, I was wrong. It says it says compound monthly, right? The 9% has to be divided by 12. So let me calculate it specifically. Okay, so the interest rate is not 9%, is 0.09 divided by 12. The monthly interest rate is, we get a monthly plan, monthly payment plan. So we have to have a monthly interest rate to match it. That's the I. Right, so it's actually 1.0075. This is also 5. That's all the B that has to be changed because the I is changing. And that should be everything we should consider. Actually, I should do. I think you should try. And that's the answer I find out. This is one of the actuarial question from the question bank. Right? We run it up and then my calculation does not have any running. I believe it's should have some running it. Right, let's answer this question for attendance purposes. And that also give us some idea on how to handle the geometric progression. Now, we should round to the nearest number in there. So this should be this is that example, I think. Whenever we have a geometric progression, I start using letters because there's the formula itself is kind of long, so having a formula in there is possible to keep track of everything. Okay, do you have any homework question you want to ask before we start today's? I'm going to talk about chapter 5 again. Any questions? Any question you get online? You just said them. Okay. Feel free to ask questions if you see. All right, so what we're going to do is continue where we left from last time. And we were working on chapter 5. We went over 5.2 already, and we're probably gonna repeat the same thing. Chapter 5, we focus on loan repayment. If you borrow money and you're trying to pay it back, there are a plan, or normally the bank accept a certain form of plan. They send you a monthly, like a monthly payment bill to remind you to pay it on time. Now, section 1 is basically introducing what this whole chapter is. We went over most of this. 5.2 is talking about the amortized loan and amortization schedule and how it's being set up. Basically, is amortized loan is when you pay the interest on the outstanding balance first, and the rest of the rest of the money in the payment will be paid toward reducing the outstanding balance. We went over this kind of example where you have you take out 2,000 loan with interest being 5%, and if the first payment is 800 after 1 year, and after 3 years you pay 1,000, and then this is the calculation for at different time point, what would the outstanding balance, what was the interest paid, and then you'll be end up having something called an amortization schedule. And it will be a chart that's showing the time, the payment, and the division of the payment into the interest and principal, and also the outstanding balance. That's what's being called an amortization schedule. And we have that also in our BA2 plus calculator if you want to use a calculator to assist your computation. The one question that we did, we can come up with a payment plan, and you finish up the time 1 payment, the time 3 payment, and also the last year. A year later, you make another payment, which pay the previous principal, previous balance together with the interest on that balance. This is something we went over already last time. Okay, this is also another example we work on. We talk about how we make up a amortization plan. This is a amortization schedule. If you're paying, there's no missing payment, all the payment equal the same value, except the last payment may be a little less. Then this is how the payment look like. So the one thing you do know is all the payment, there's all in amount of $2 until the last one is a little bit less. And having that, all this payment in the R is given. So we don't know the outstanding balance. So you have to find out the current value of all the future payment, which will be the QA-1 plus RVN. So the balance at time 0 is your loan balance. And then with the same idea, all the balance can be calculated in the same way. Okay, so so the balance can be calculated because the payment is all set. And then with the balance given, then you take your balance, multiply by I, then you have your interest column. Once the interest column is all set, you use your payment column value minus the interest column value, which gives you the principal value. So systematically speaking, this is how we set up and be conformed with what each column is supposed to be. Any question? So that one, and we went over that one, and we also have another example on come up with a table. In this case, we have the QQR. In this question, the first 3 all equal Q with 5,645.75. The last payment is a R with 4,645.72. So that will be the amortization schedule, and we went over most of the calculation in more detail last time. If you want to know how those number comes up, you can look at the video from last time. So I'm gonna probably skip the details as we went over this one by one. Any question? Okay, having that ready, we also have a plan for how we do those calculations. Use a BA2 plus calculator. Make sure it's in envelope, make sure you have the payment per year and so P/Y, C/Y all set up as equal 1. And then the middle row of those Y key, you want to identify, and equal to 4, present value equal to negative 220,000. The payment all equal to 5,645. And then you can calculate the I/Y, calculate the interest per year. And then open the amortization worksheet. And then you can display, which you can then display whatever balance or principal or interest you wish to know. And that's how we use the calculator to do it. Okay, I think this is where we stopped last. Okay, so we went over this example. This is the last example we're talking about. We'll continue from here. So we're going to try to finish 5.2, possibly move on to 5.5. In this question says on May 1988, the family purchased a home for 308,000. Their down payment is 46,000, and therefore the rest has to be financed. They were doing a 15-year amortized loan. The nominal interest rate is 5.55% convertible monthly. How much interest did they pay in 1993? Assuming their payment have all been the first of the month. The first payment was on June 1st, 1988, and that there has been no additional payment beyond the scheduled one. So here it's really what we're trying to calculate. The question is something that we haven't really focused on in the previous example. So in this question, we want to know how much interest we pay for that year. So the implication of this question is we're actually not paying the same amount of interest every year. The reality is the time in the first year, second year, third year, the earlier the time is, according to the amortization schedule, you pay more interest. I hope that you have that. The reason is your balance is high at the beginning. The balance multiplied by the annual interest. Of course, the annual interest is paid a lot, right? Right. As the balance reduce, the balance, outstanding balance multiplied by interest will get less and less. So in the end of your loan schedule, you're paying more and more of your principal, less and less of the interest. But at the beginning, you pay a lot of interest because your balance is high. So anyway, so we're gonna focus on 1993, and then here is where I draw the timeline, and we want to find out in 1993 what happened. Okay, so how many months since May 1988 to January 1993? The number of months will be 93 minus 88 times 12. And then January and May, you're going to take the January, the 1 minus 5 to get the number of months. So there's 56 payments for that. Any question? So then we're going to start looking at, if we're focused on the year, how much payment is made in that year. We're paying. This calculation actually apply the total number interest from 56 to 67, right? The 56. So this is what we are using. We're using the interest formula in our amortization schedule, which is over here. Look at the interest column. That's what we're gonna focus on. Yeah, we have we're using the interest column as the foundation of calculation. So we have Q times 1 minus V to the N minus P power, and then R times IV to that power for the equation. This method rely heavily on our understanding of the amortization schedule. So if you are a little bit rusty on that, this method may not be the best one. But it gives you some starting point. So essentially, in that year, we have 12 payment. So then included in every payment in that year, there's interest, right? We're calculating every interest and add it together. We're adding 12 interest there. So in here, we got to know the Q is your annual payment, which is the total loan balance divided by A180. this is the 5-year plan, 5-year monthly payment plan. So there's 180 payment. So 268,000 divided by 8180 give us the monthly payment plan. So that's our Q calculation. V is common. And then we're making monthly payments. So the monthly interest rate, nominal interest rate has to be divided by 12 to get monthly interest rate. We have our number. And so all the number involved in the calculation of the total interest has to be calculated first to finish this. Any question? I realize even knowing the R, trying to figure out the R takes a little bit more time to figure out every piece of it, the I, the V, the R, the Q. And then the rest of the calculation is this. So this calculation really is a little bit more time consuming. Consider how many calculations we have to do individually. So this is method 1. And there's another method I think makes more sense. It's a lot easier to manage. So the second method is based on the fact the amount of interest paid during the whole year is equal to the total amount that we paid minus the money that we are paying the principal. So this method is not following the interest formula. Instead, they focus on the actual payment and minus the principal that we paid. So payment minus the principal will be the interest. So how much did we pay in the principal? That depends on how much decrease is in the outstanding balance, because the differences in the outstanding balance is caused by reduced by the principal, right? So deduction in the outstanding balance will be the principal payment. So basically, the total interest paid is, you got 12 payment. Every payment is 2,147.7. So that's the total payment. Right, the one at times 12 is the total payment. Then the outstanding balance is a little bit problem. So we have to do outstanding balance of 67 minus outstanding balance of 55, because there are 55 payment before that year. So here are the calculation. Now, in 1988, there are 7 payments, and then before the 1993. Including 1993, there's 12 payments per year. So altogether is 60. So 60 plus 7, that's 67. But not including 1993, that will be 4 year. 4 times 12 plus 7 is 55 payment. So we get those outstanding balance there. Outstanding balance of 67, outstanding loan balance of 55. 67, 55. Just focus on those calculations. Now what we do, the rest is try to figure out the outstanding loan balance using a retrospective method. So you take the loan balance, multiply by the interest rate to that time frame, minus the Q times SN to calculate their total accumulated value. So your loan balance minus the money that you paid is your outstanding balance. Once we find the outstanding balance, subtract them, which give you the principal paid. The total number payment minus this payment paid is the actual interest. So that final answer will be the same answer as before, but it's definitely more manageable. It's the same answer. The 10,922 is the interest paid in that year. So basically, we paid a lot of interest in that year. Any question? So this is one of those questions, and give us some way to handle when we focus on the yearly interest, how we do it. So basically, two method. All right, and then there's a way to do it without doing the extensive calculation, and that's kind of the reason why people want to learn how to use a calculator. It does save a lot of time. If you put in the number payment, which is 180, put in the interest rate, which is 5.55 divided by 12, and then put in the present value of negative 262,000, future value equal to 0, calculate the payment, you get the same payment amount that we had for Q. And then set up that as your payment and you calculate the future value, you're gonna see the future value is negative. So given that, you can start calculating a amortization table. We can find out the value from the time 56 to time 67. So here you can start saying those notations, meaning the 56 is the initial time, and then you enter, which scroll down. So 56 enter the number into the calculator. The down arrow moving on to the ending time. So the ending time is 67, then you enter the ending time, and then press 3 arrow. You will find out the interest paid all together in all those payment from payment 36, payment 56 to payment 67. The total number interest is calculated by the. So it's really a lot faster than we have to do now. Any question? Basically, if I can avoid using or depend excessively on the calculator, I will try to manage. But this is one example. I would prefer using the calculator because the amount of time we can save is a lot more than we can imagine. It's without the calculator. All right, so next example in this section talk about early payment of a amortized loan contains significantly more interest. Okay, so here says if you have an amortized loan made at an effective interest rate of 6.6%, is to be repaid over a period of 15 years by annual end of the year payment of 1,800. What proportion of the loan total interest is paid in the first 5 years? So basically, it's kind of echo what we're talking about at first. In the first 5 years, like year 1, your interest has to be annual interest rate multiplied by the outstanding balance of that year. And then balance at the beginning will be a lot, which is why we have to pay a lot. So we're trying to figure out how much interest, what proportion of interest are being paid in the first 5 years. So here we are. In this question, we are paying end of year payment of 1,800. So we have continually the same payment. There's no deduction in the last payment, so 15 payment of 1,800. That's going to be our schedule, assuming Q equal to R. And you can kind of compare that with the Q not equal to R with our last table. When Q equal to R, it saves a lot of trouble. We would not have to, I don't want to go back. We don't have to worry about having that R or RV. The discount of R is no longer in formula. It's more standardized way to look at it. Now, how we come up with the table is similar as before. First, the payment are identical. They're all Q. Q is the 1,800. So the payment column is all set. And then the last column is all set. The balance, the outstanding balance is the present value of all the future payments. So QAN, QA minus 1, QAN minus 2, and QAN minus K, and so on. Of course, the last balance is supposed to be 0 after the nth payment. So the balance column are like, it's all in the same format. And then work on the rest of them. If you take the balance column multiplied by I, remember the formula for AN is 1 minus VN over I. If you multiply by I, now you have your interest column. So all the interest column have that factor 1 minus V to the power N minus K. So now the interest column is all set. So you take your payment column minus the interest column. There's your principal column. So now you can see the principal column also have a very standard form. So whenever the Q equal to R, the amortization table become a lot more consistent, a lot more formularized, and it's kind of easy to remember this formula compared to the last formula when the Q not equal to R. So that's going to be our tool or formula when we try to work out this example. We're trying to look at what portion of interest is being paid in the first 5 years. So look at when the time equal to 1, 2, 3, 4, 5, and then you can look at interest the interest in the first year is Q times 1 minus V in. Second year is Q times 1 minus V to the power n minus 1. And the fifth year will be Q times 1 minus V to the power of n minus 4. So we can see the formula for the first 5 interest, and then we're going to look at the total interest for the first 5 years. And those are going to be what we're going to follow. Any question? Okay, so then we find common factor and look at all the V's. There seems to be following a geometric sequence, but you can also think of this as subtraction of annuity formula. If you have a way to calculate those annuity formula easily, but I would put in the V as 1.0. What was the interest rate in here? Is 6.6. So you just put in the interest I for the V equal to V to the 15 power, V to the 14 power, and so on. There's only 5 numbers. It's not that hard to do it without the A and A15, A16. So we have that will be the answer to this question. That's calculation of the total interest. Now we need to know the proportion. The interest that we have here is over here, 5,662.995. That's the amount of interest that we paid in the first 5 years. Now, what's the total interest? Total interest is a loan amount, so 1,815. Discounted out of all the payment, we have 15 payment of 1,800. Subtraction of those who give you the total interest. So our total interest is 10,183.39. And you can see we're paying 5,000 interest in the first 5 years. And this is a 15 years payment, which means in the first 5 years, for the 15-year loan, you're paying almost half of all the interest in the first 5 years. It's basically saying we pay a lot of interest at the beginning of the loan. Any question? And you kind of know why, because you put interest first, you pay interest for every year. This is how we do it with a calculator. We will put in the number payment per year. How many payment we got? 15 payment, 15 year. But which each year we're paying a payment amount 1,800. We put in interest rate of 6.6. Future value is supposed to be 0. We can calculate present value, which gave you the loan amount. And then you go second amortization. And from here, you can figure out recalculating. It looks like we're calculating the interest rate. It's not the interest rate, it's a division. That's the proportion that we're calculating. So we calculate the present value, which is the loan amount. And then in the amortization table, we went all the way to 15. And you push 3 arrows to find the total interest. And then you go back down to find 5, and then with 3 arrows. So basically, we find that 2 of the total interest and divide them. And that's why the last number should be the division of the 2 total interests. It's the total interest for 15 years, and then the total interest for 5 years. Divide those 2 together last year. So that's basically how you calculate it without writing it down. We pretty much rely on the calculator. Any question? All right, 5.3, the title is called the sinking fund method. So this is kind of different than the amortization plan. So we're not paying equal amount anymore. We're not following the amortization payment schedule. Instead, escape that. All right. What the sinking fund does? Actually, you will wait until different one than. See. Sinking fund is different than the amortization plan. So instead of paying interest, a little bit interest, a little bit principal every time, you will pay your interest, and then you wait for it's called a sinking fund. You use a separate account to accumulate all the money you were supposed to pay off the principal, and you then use the accumulated value in that separate account to pay the balance of the. So you would have a fund, a separate fund for the payment of your loan. Finish editing the one that was working. So it's going to use this one and this. Right, this is a new file. I was using. Let me get more example prepared for us to finish talking about it. And for some reason, the last time when I was going over, I skipped that section. Done something different to it. All right, let me explain 5.4. It's more closely related to the amortization schedule and payment plan. So sinking fund is kind of a different scenario, a different plan. All right. So 5.4 continue the topic that we had earlier. If you have an amortized loan and what if you change your repayment pattern? So here, if we are changing the payment pattern, instead of paying Q and Q and Q and Q and then R, so instead of paying almost equal amount in every payment, maybe you have a different way. And we are doing that in our weaker question. The one that we were doing this, all right, we were talking about having a decreased payment plan. You can possibly have an increased payment plan. They're all possible. So if we do have a change, then the outstanding balance will still be another issue, and we wish to have a way to handle that. So here we're gonna introduce a few more notation just so we can have a more nominalist way to compute them. PT represent the payment amount at time t. So no longer using the Q because we're not assuming they're the same thing anymore. BT represent the balance at time t. So BT replace the outstanding balance notation I used to write OLB in the past. That's just the BT balance at time t. Okay, so BT represent the balance at time t immediately after the payment PT. So assuming that you did pay the payment at that time, right after that payment, what's your balance? IT denote the interest rate for the interval t minus 1 to t. So that is consistent with the interest that we had in chapter 1. So now BT would represent the last balance multiplied by 1 plus IT. So you're going to take your interest plus 1 is the gross factor. So BT minus 1 times 1 plus IT will represent the current value of the balance. And then that balance is from past. So your balance right now is after you made that payment. So you have to minus the payment PT to get your current balance. This is at the same time as the payment. So PT do not have to be discounted or accumulated. So BT itself is not multiply anything. But BT minus 1 is the past time. So there's a gross factor to it. That's the BT formula. Any question? So now we have other topic in this section that we were not mentioning in 5.2. And most of them are in the same idea though. All right, so let's see, with example, the 5.4.2 is talking about an amortized loan with level payment of principal, which should be actually what we have in 5.2, but we're just trying to replace and be consistent with the notation. Okay, so Adam takes out 20,000 loan for 10 years at level annual payment. Interest will be 5%. At the end of each year, he pays 2,000 in principal, which is 1/10 of the loan amount. You can say 2,000, 20,000 is 1/10 of the loan amount along with interest. Find the formula for PT. So in this question, we identify there could be a payment plan PT. Well, isn't PT supposed to be constant if it's always 2,000? Okay, so here where's our solution? So PT is the payment amount at time t. So we're trying to figure out a formula for PT. The balance is going to be reduced. 1,000 amortized loan with level payment of principal. Okay, I see what's going on here. So we're saying we are paying 2,000 in principal. So we're not saying we are paying 2,000 total. We're actually trying to guarantee every year the principal or the outstanding balance will be reduced by 2,000. We okay there? So then that will guarantee the changes in the balance is consistently linear. So every year is 2,000 minus 2,000. So year after 1 year is 20,000 minus 2,000. After 2 years, the balance is 20,000 minus 2,000 minus 2,000. So that will be the formula for what we call the BT. So in this question, we have we're trying to make it easy to calculate the balance. So we're trying to find a way to guarantee the balance is reduced by 2,000 every year. And that will cause a little bit more complication on the payment. So if the principal is being equally deducted every year, then the payment cannot be, right? So we're trying to figure out how much do we have to pay every year. Since we're paying at least 22,000 in the principal, and then the principal plus interest would be what we paid each year, right? So the actual payment should be the 2,000 plus that year's interest. So following that idea, we're going to apply the relation between the BT and PT. And if you look at this formula, it's actually kind of recursive, right? You calculate your balance at time t based on the balance of BT minus 1 and PT. So you got to know PT in order to find out BT because BT is calculated using BT minus 1 and PT. So in a way, we have to work out the math in order to figure out how do we come up with the proper formula for PT. So here we are. Relation using the previous formula is BT equal to BT minus 1 times 1 plus I. We have an annual interest of 5%, so 1.05 multiplied BT minus 1, and then minus PT, that's our formula. So solving the PT from this formula, PT equal to BT minus 1 times 1 plus I minus BT, right? Right? So then in a way, this relation 5.4.1 is going to be our formula for PT. Okay, so we're kind of, the whole point of this section is that what if you are reaching other goals? But if you are not planning on getting the same payment every time, based on your objective, you may have different design of your payment. So this question that the BT BK is the balance. The balance that every time K is 20,000 minus 2,000 K. So we have a formula for BT minus 1. We also have a formula for BT. All we have to is substitute T or T minus 1 into the formula BK. And then we can start saying the calculation, the like term are combined. Then we have a final formula, which is 3,100 minus 100 T. That's our formula. Any question? That will be the plan. Another way to look at it is going to be figure out the interest per year. And then all we have to do is take the 2,000 plus the interest per year. That's the payment. But then again, the interest per year is not consistent. I guess this calculation is easier since this is going to be the main formula for this section when the payment are changing from time to time. So the payment PT follow the relation BT and PT. Right, so that's our first example. We will have when we have a requirement of how much principal we're paying each time. That relation causes us to have a decreasing formula for PT. As time goes on and on, we pay less and less because of consistent reduction of principal, and the payment gets less as time gets. So, right. The second example in this section, we have a amortized loan with payment in arithmetic progression. Theoretically speaking, our bigger question is when the amortized loan, when payment is in geometric progression. So this is a one example. We have arithmetic progression of the payment. So let's look through the example. We take out 20,000 loan for 10 years and level annual effective interest rate. So the interest rates suppose are not changing. So starting here, we have a sense that maybe the interests are changing sometime, and that will cause a little bit complexity in how we calculate the value or the balance. Her original payment is P, and then her payment increased by 200 each year. We want to find the P. Okay, so again, we have, we're trying to find the payment. The original payment is P and increased by 20 per year. So that's really the payment plan. Payment would be P plus 2000 T, right? That's going to be the PT. And then, we know the final balance after 10 payment should be 0. So we can use the balance as a way to figure out relation for P. I'm going to do it. This is the arithmetic level plan. So all the present value of the payment in arithmetic progression should equal to the current value, the loan amount, 20,000. So 20,000 equal to, this is IPQA formula. We have arithmetic progression. So we may have to apply that formula that we had in 3.9, right? 9. We handle arithmetic. So PQA is what we are applying 10 payment. This is the current value, present value of our future 10 payment. The first payment is P. We don't know it, but we know the Q. The Q is an increment, which is a 200. So we enter all these numbers, having P as the unknown. We can then solve the P from this question. So this example actually apply the low amount input or not 52. find the IPQA formula from 3.9. It's really solving the equation we set up at the beginning. And then the rest is all algebra. Any question? This example, the calculation is if you are trying to use a risk regression, how much do we have to pay at first? So basically, the section handle a couple of scenarios. If you have a plan and we determine a reasonable way to work it out. This question saying if we have a geometric progression, how would the payment? Civic also take out a 20,000 loan for 10 years at a level annual effective interest rate of 5%. We see level, meaning the interest rate did not change, they'll always be 5%. His payment grow by 20% each year. The question is to find the amount of the first payment. So we have the progression, we have the interest rate, and basically it will follow similarly like that one. This is a geometric progression. So the 20,000 equal to the present value of all the future 10 payments. And this, like how we treated all the 3.8 questions, you're gonna write out all your payment and have to work out a geometric sequence of all 10 payments. And that's how it looks like. It's paid by the end of the year, so it's end of year payment. Right, so then we're using a discount factor. So then the first payment discounted to a time 0, and it's all discounted to time 0. And the 1.2 are the geometric progression, 20%. So that's what we have, the 20,000 to the geometric sum of all the future payment. And then all we have to do is solve the P1. P1 is the first payment amount. Any question? So a little bit fast, but then we try not to focus too much on chapter 5. I only assigned one assignment, which is around 5.2. Maybe some of the assignment actually echo what happened in 5.4, just like the flicker question kind of should belong here in 5.4. But these have a very similar reasoning, apply related material that we learned in chapter 3 or 5.2. So hopefully it won't be too hard to do. And I won't assign too many assignments for chapter 5, but at least we have to have some experience with these examples. This example have repaying a loan by paying 4 times the interest due at each payment time. That friend also takes on 20,000 loan at a level annual effective interest rate 5%. She makes annual payment that are 4 times the interest due until she can make a final end of year payment of no more than 2,500 to pay off the loan. When does she make this final payment and what is the amount? Annual payment that are 4 times interest due. So we will calculate the interest for that year. Also, the interest time 4 will be that payment until she can, we know she can make an end of year payment. So she continue paying all those interests until she reduced the payment to be less than 2,500 to pay off the loan. So now we have to figure out the time when the payment can be reduced, and we also want to figure out the actual quantity of the final payment. So we kind of try to figure out the interest rate, right? 4 times the interest. We focus on the interest relation here. So you're gonna see the annual interest is 5%. So 4 times the 5% will be 0.05 times 4. So that's 20% of interest per year. And that will be her payment until the final payment is less than 2,500. So that gives us this relation between the PT and the last balance. So, and this is why we have the first equation, our payment amount equal to 20% of previous balance. And with that relation together with BT equal to BT minus 1 plus I times minus PT. And that will give us the relation that every balance will equal to 80% of the previous balance. So the balance will be in a geometric progression, and the balance will get smaller and smaller as time goes on. BT equal to 0.85 of BT minus 1. This actually means as time get bigger, the balance gets smaller, which makes sense. The balance is supposed to be increasing. Right. So having that condition there causes us to have relation between all the balances. So we're essentially this requirement saying make an annual payment that is 4 times the interest due. It indicated that the payment has it's a proportion of the balance because we're paying 4 times the interest, and interest is interest rate multiplied by the balance. So now the balance is also a fraction of the payment is a fraction of the balance. So we have these relations saying that now we have a set formula for BT and BT minus 1. So PT equal to 20% of BT minus 1. So BT now equal to 0.85 BT minus 1. And therefore we can keep going until we reach down, until the balance is small enough. So we have a BT minus 1 that equal to 0.85 to the power T minus 1 multiplied by 21,000. And then the final payment is to be less than 2,500. So all we have to do is to make sure the balance is below that, because that balance is supposed to be the last payment. So that allows us to figure out the time, and turns out the T 15. So by the time T equal to 15, the last payment will be enter 15 as our T in that formula. Our last balance should be our last payment. So this causes us having a schedule for all the payment, because we also, in the meantime, we have a schedule for the balance. Any question? So the intention of having the payment being a proportion of the interest made it also a proportion of the balance. So then we can apply the relation which says BT minus 1 times 1 plus I minus BT. That formula is most essential, and we can use that recursive formula. So that is again a special scenario to connect the payment with our balance formula. Okay, so basically 5.4 handle a couple of special situations, and 5.4 and 5.2 are two of the focus, because amortization plan is the most common way to pay off the loan. And I feel like I should write up a couple more examples for the sinking fund. It would apply the annuity formula that we had in chapter 3, and looking at the relation between the two accounts, the balance in your loan and your sinking fund payment. So let me try to write more example and then come back with that one so we can have some understanding of the sinking fund. I don't see any question in the actual exam that involves sinking fund, but since it's there, a couple of times we'll talk about it, so maybe we should at least know the notion. So in the meantime, by now we should be able to work out the homework question for chapter 5. The only assignment for chapter 5 is 5.2 about the amortization plan. Most of the topic are how to calculate total interest or total interest per year, how to calculate principal for that year, how to find outside balance. And that's pretty much the common kind of question with loan involved. Any question? Now, the yield rate is interest rate involved in the payment of loan is the same as the yield, the interest rate we're talking about in chapter 3. So I'm probably not gonna repeat this. And that should be it for today. And then other than the 5.3 that we skipped, the rest of the chapter 5, it will probably end there. Because I feel like this section repeat what we did in chapter 3, so we'll probably skip that. And then we'll probably, if we have time, we'll go over to chapter 3 and move on to chapter 6 this week. And that'll be it for today. And then please try to find time to catch up with the homework that we assign on. See it already under 5.2. So 5.2. It's open today, right? That will be it for today. Thank you.
Yeah. Will you be in your office later?
I will. I have office hour in the NASA right after this class, and then later I'll be in my office. Yes.
Okay. I just had a class right now.
I see. I see. Yeah. I definitely will be in my office.
I think I did it right. Maybe double check.
The last question, you're still working on it? Yeah.
So.
Okay. Okay. Let me double check my calculation again, and then I write it up a little bit nicer than my on the spot. Then my writing was kind of awful, but maybe I'll type it out. It was more organized.